Good afternoon to everyone. I am Thiago Setti. I know many of you, we have had the opportunity to talk in other occasions. We've been for a long period of time in the market. Now I'm a consultant from NUITEC. I am member of the program committee of the PF, and for many years we've been cooperating with the IX initiatives. And I am very proud to participate in this event, to congratulate the organization because this is excellent. And these events strengthen the community and the evolution. So let's start. This is an interesting subject, more related to infrastructure. It's a bit more basic. It's not very advanced, but we can cooperate with information that people have or they didn't have access to. So we can help you to clarify questions in the evolution of each one of your networks. When I saw the amount of time that I had to talk, only 30 minutes, I thought, well, this title is too presumptuous. Everything you would like to know. You can't talk about everything you want to know in 30 minutes. So we will talk about a number of points. And now here I will pose questions, and I won't go into details because I really don't have time. And I haven't even started projecting my slides. So a brief introduction. I will skip the introduction. Optic transmission. The transmission and optic fiber, light, Wdm Solutions. And you can see it's not DW, it's Wdm, and you will understand why. And a last point about the evolution. Okay, let's skip the merchandising part. Optic transmission. So we will talk about this. And what is it? Number one, is it optic fiber or is it optic or otic? In literature, we read optic and sometimes without P. This is in Portuguese. If we see the origin of the word otic is related to the ear, and optic is regarding the eyesight, vision. So when we're talking about light, optic transmission, we should always write with P. But there was a review of the Portuguese rules, and they say that when you don't pronounce the P in the word, you don't include the P letter. So we can continue writing both ways, optica or ótica. This is just a matter of Portuguese language. And I like to write it with the P because I'm used to it in English. Is it fiber or fiber? Fiber or fiber? American fiber or British fiber? Both of them are right. It's American English and British English. American English, it's fiber, and British, it's fiber. So when you read an article, depending on who writes, you will see fiber or fiber. So these are just some things that I brought. And this is a good question. Is the fiber hollow or is it whole? Who thinks it's hollow? And who is just in full? So everybody thinks it's filled. It's not hollow. And it's true. It is not hollow. No, it's not hollow. But this is going to change. So the fiber is a piece of glass. It's made of silicon dioxide. It is a component that we have anywhere in the world at a low price. Most of the fibers are made of glass, but we do have plastic fibers. And in some very specific cases, you have this for some data centers where they have plastic fiber and they can transmit the light through it. And what is light? At the end of the line. What are we transmitting here? This is radiation, magnetic radiation. There is no major secret here. I am not going to go into physics, but you don't need means to transport it. It goes through void, water, material, any material, and it has this property of just going through, and as it is an electromagnetic wave, we have a speed measurement. The speed measurement follows a history. Not always the speed of light has been constant. The current wide of 299,792,468 kilometers per second wasn't like this. We have a history of the evolution of the speed of light. And this has been evolving throughout time until we reached an 83, and we defined this parameter here. And nothing stops new researchers to tell us that there are new evolutions, and we will have a more accurate number of this information regarding the speed of light. And this directly impacts the telecommunications where we use light. We transport up through optic fiber. So the speed of light, when we use the speed of light, we use this variable as a key point. My next question is, now that we know that light is an electromagnetic wave, what is faster, light or optic fiber? Because the market practices they say that the concept of speed does not mix with the concept of capacity. When you have a circuit of 10, this is capacity because velocity or speed is the time between you leave point A to reach point B as a summary. For us from telecom is latency. You have to be faster. When you think about speed and latency, which is faster, radio or fiber? And who thinks it's radio? Well, some people are in question. It's half-half. So now you will understand that it's faster and has less latency. What? Radio. Because of this, the light propagates itself through the means. There is an index of refraction, the speed of light over that mean. So when you transmit light over the void, the real speed is the maximum speed measured by the human being regarding the speed of light. And when you go to the air, our atmosphere, it is 99.9% of the standard. Speed of light, coaxial cable, 87%, and optic fiber, 68%. The speed of light and optic fiber is not 299,792,458, it's 203,858,871 kilometers per second. It's 30% slower than when it traffics through void. So if you place a radio computer, the latency will be 30% better than fiber optic. If your concern is latency, then you will have to work more with radio. But obviously, we know that radio has other characteristics that don't meet our capacity spectrum. But when we think about latency, we have to think about radio because it uses the air. So when they were talking about CDN, the latency, the ideal is to do it with radio. But we won't have bandwidth, so we know that this can't be used. When you sell this to a customer, you have to be very careful. Oh, fiber is faster, less latency. Even the coaxial cable is better than your optic fiber in terms of latency. And regarding optic spectrum, this is another curious thing. The optic spectrum is measured in length of land. It has a visible spectrum at the human eye. Here at the end you have purple, and then you have ultraviolet. Here you have red, and below red, infrared. So all the optic fiber where we use our telecommunications of telecom, but what we use in telecom, they are in the spectrum of infrared between the window of 850 and 1625. People have seen this. They say, oh, well, there's 1310, 1550. Telecom uses the spectrum here. Therefore, it's not visible to the naked eye. And then we have this window to use optic fiber of the spectrum divided by windows. This is a chart from a common optic fiber defined by ITU that defined windows of operation within the infrared spectrum. You have the first window of 850, where you have multi-mode, the multi-mode LEDs, the second window that is in 1310, and the third window for DWDM, that is a window for C-band. You have band OESCLU. And how do you break up the air spectrum? You do the same thing here. This chart here demonstrates this very clearly. And remember that I said that you could not see light. And when I go in front of how can I see sometimes a little dot here, a red dot? There is always one. You look at it. Oh, let me just see. It's not recommendable to look at it. Although the lasers can cause damage to your eyesight, especially the more powerful ones, the ones that you can't see multi-mode are LED, so they really don't affect you that much. So why can I see this? This little dot, in reality, you're not seeing the 850 light. What you're seeing here is a slight interference that we have in the 850 frequency that goes to the 750. This is the light displacing it inside its spectrum. So you're seeing something between 650, 750. Some people can see it. Some people that can't even see it. They can't even see the color, tell the color.
E vamos falar sobre potência ótica, o conceito.
Optic power. Optic power is the intensity of light. How weak, how strong is the light? This is something that we use in telecom to carry out a correct measurement. It's generally done in milliwatts, but there is an algorithm ratio with decibels to have an accurate reading within the algorithm scale that we use, the dB, that is from decibels. When we talk about the signal of optic power is 1 dB of 1 milliwatt, 1 dBm, that it was 1 dB regarding 1 milliwatt. The 1 milliwatt is absolute, the 1 dB is relative. The absolute value is the value that you see here. The relative value is what you gain or what you lose. How much do you lose? You lose 3 dB. The amplifier has a gain of 20 dB, but what is the exact measurement? That is not relative. How much does this transponder transmit? The value is absolute, and it's in dBm. When you're talking about gain or losing dB, when you're talking about transmission, measurement, power transmission is dBm. So we generally confuse this concept, but this is the correct terminology. And here we have an attenuation table, just for you to understand this algorithm regarding losses. Here we have the loss. This is the loss in dBs, the power percentage, and what does this represent? When we talk about 1 dB of loss, we have 79% of original light. When we talk about 3 dBs, this is half. It's 50%. So if somebody says that they have a loss of 3 dB, it's not little, it's a lot. It's half of the original power. is lost. You only have half of it. And now you're going to algorithm scale, and let's see where we'll end. With 21, you have 1% of your original light. So when you have 8 kilometers, 120 kilometers, trying to reach, we have 21, 22 dB. It's not 21, 22. Because 24 dB, the difference to 21 dB is vast. With 24 dB, you have 0.3% of light working. Sometimes you see a data sheet of an optic model that has a sensitiveness of 23, 24, or 30%. They can only see 0.1% of light, and it still works. So you can see how the optic network is and how you have to take into account these measures, because 1 dB is a lot, and this represents in practice a greater investment to maintain this, and so it works properly. And here are some effects from the fiber. When the light goes through fiber, I'm not going to talk a lot about this, they suffer some effect. It's not only an attenuation, it's the loss of power of the signal, but there are other effects, that is chromatic dispersion, the distortion of the pulses, and I could spend an entire day talking about these effects. And then the second thing that is important is the effect signal noise. But these are the three most important ones when you're going to design an optic network. The signal optic noise, this happens when you have an amplifier. How do you resolve these effects? The problem of attenuation. You resolve it in implementing an amplifier. It can be an EDFA. Sometimes it's called Pred, Booster, and Raman. That is another type of amplifier used in WDM networks to amplify the light signal that suffered attenuation. Chromatic dispersion, you put a corrector of chromatic dispersion, can be physical or digital, or you can do this digital. You have a DSP that does it for you and offsets the dispersion in an electronic fashion and not in a physical causes. And the effect of the noise, well, the noise is inserted when you have an amplifier. Generally, when an optic signal has to go through an amplifier to be amplified, the amplifier is inserting new photons that in a simple way are copying the frequency of the photons that arrive at a lower frequency. And then they insert photons of the wrong frequency with distortion, and this is noise, and this is detected as noise and not as signal. Although you have a great amplifier, the greater the amplifier, you will have more noise, and then you will have just on the only side, you will have noise, and you won't be able to differentiate what is noise and what is signal. And this here allows you to see what is noise and what is signal. So the further you go, the more amplifiers you have, the more noise you will have. One thing would be to regenerate the signal. So you use a signal with lead noise, you bring it to the electric world, or you have some mathematical algorithms that are algorithm corrections, and you can correct the algorithms. They will detect the signal, the noise, they will detect the beat, but they have a subsequent mathematical account to identify if the beat is right, and if it's wrong, it corrects it. And this has a limit as well. And we also have the nonlinear effects. And this is a funny story that we learned about in the GTR of Rio de Janeiro 4 years ago. There was a technician from GNP that said, every time I'm going to work with WDM networks, we know about the linear effects. But when we have problems with the equipment, when it doesn't work, you ask the the supplier, they say, oh, this is a nonlinear effect. Nobody explains. They don't know what it is. It's nonlinear effects. It's like a virus. It's like a virus. It's a virus. It's a virus. So it's a nonlinear effects, but nonlinear effects, they are studied, they're known, they're complex, highly complex. And basically, if you try to summarize the linear effects, they're connected to power in many channels. When you have many channels in one fiber and you have an effect, to diminish the nonlinear effects is to diminish the amount of channels, powers, and then you lose distance here. And this becomes a challenge because here you will have to do the engineering of a link of a WN. And here we have the most common optic fibers and some that are not very common. The GM652 has a standard attenuation of 0.22 dB per kilometer. It's what it attenuates on band C. Remember band L, O, the first window. Now band O is 1,310. Here we have chromatic dispersion, band O, band C, and attenuation is different. I didn't put the attenuation of band O. The attenuation of light is different in band O, C, or E. My band C is very common for DWN systems. You can see that we have high quality fibers. They're of special manufacturing. When we're used to 22, this is standard. It has to have 0.22. This is standard. As we're engineer, we say a 0.25. It's a K factor just to guarantee. But you have fibers today that are purer and can absorb less light. The record that has been published by Sumitomo is that I achieved 0.148 dBs of attenuation per kilometers, and it has more dispersion than the common one. Now, Wdm Solutions, we talked about optic transmissions, the effect of fiber, and what kind of solutions do we have in the market in order to use a number of channels with the same fiber. So what is Wdm wavelength division multiplexing? It's Wdm. So if you were to have a number of channels, these are a number of channels of 100 gigas, and A and B. If you don't have Wdm, they need each one a channel. If you have a Wdm system, you can place each one of them in one color. One color for us is wavelength, and you can multiplex them through fiber, and then you deliver these channels. With one optic fiber, you're able to pass a number of channels that you had to do individually in the past. This WDM. WDM has two more common technologies, Cwdm and DWDM. And this according to the spacing, how close one wavelength is to the other. Cwdm is in color and D is dense. The denser the spacing between one of the other, it's lower, so you can place more capacity here.
A very important piece of information here is that within the CGI.br, they use just band C, whereas the other one, the whole spectrum. Such a space between channels that is standardized by ITU, which divides that space between 100 giga, 6 giga, 100 and 125. Now that's no longer a standard. There is no need to have a fixed grid. They call them different names, upper channel, where you no longer use the fixed grid, and you bring them together, and you no longer have a grid. That is the concept of flexible grid. Is that always unidirectional or bidirectional? Both. You have DWDM, which transmits by one fiber and it receives by another one. And you also have DWDM bidirectional. You may have a total bidirectional system. One single fiber can be responsible to transmit and to receive. You use some of the wavelengths to transmit and some other ones to receive it. And you can have DWDM system in a simple way with bidirectional fibers. Do not ask IX to do that for you. That's going to be very worksome. DWDM system consists of several alternatives, such as transponders, those equipments which will translate the gray signal to a colorful one. There are multiplexers. And in the middle of the way, you have the OADM equipments where you may remove one of them and let others to go through. That OADM can be fixed or can be adjusted, can be set it up. What is a transponder? What's the difference between transponder and mixponder? A transponder is one-to-one. You take a gray signal into a colored signal, and the mixponder is a device where you can multiplex different services, all those on the left, and then you can take all of those signals to one single channel. Transponders evolution. The older generation, they were 10 giga, and now they are much more powerful. They are coherent with different modules, different colors, different detection, which is different from the direct detection on and off. That was a great improvement for the transport world. And here is a table with modulation capacity, the same one that you use on radio. There are some which are even more advanced than that, but the WDM systems, they are taking that to optical fibers. Minimum SNR, spectral efficiency, and space. So the bigger the modulation, the greater the capacity. But the minimal SNR increases. With that, I may reach much shorter distances. With the 6 giga channel, I live here. The longest one I've seen lives Maldonado in Uruguay, and it reaches Boca Raton in the United States. A total of 12,000 kilometers, whereas a 600 giga channel won't be able to do that. So this is a type of fight that we have to solve. Capacity and rest. Ideally, if we could cross the whole road with 600 giga, that would be awesome, but physics does not allow us to do that. So that example from Uruguay to Boca Raton, submarine transport, the fixed system versus sub. The submarine system usually is end-to-end, point-to-point, no regeneration. There is no site, no station to place a regenerator. The sign goes straight through it. The grid here can be fixed or variable. It's no longer necessary to be just fixed. You have constant power amplifiers. Every time that you have a sub-cable, you have to fill up the whole light spectrum. Those amplifiers, they have a fixed output, and you need some signal for that. Of course, you do not start with 12 tera. You inject some noise, a white signal, just to occupy the amplifier. And their shelf life is of 8 to 10 years, whereas the submarine, 10 to 20 years. Why a sub-cable has more than 8 fibers? Why don't they release 144 fibers instead? Do you know the answer? Well, the sub-cable, as there are amplifiers within the cable underneath, you need energy to amplify that signal, and there is no energy there, right? And that energy goes through the cable over that copper cover, The cable is covered by this copper lead, which uploads energy, and you need energy at the edges, and that's not available. There is not enough energy to be taken to 144 amplifiers that we have inside the cable. That's the reason why cables usually they have 6 to 8 pairs. And last, evolution. New technologies are coming. First, the use of band L, multi-flows, and the last one, I'm sorry, I just missed. Let's see when he goes back with the slides. But band L, that's not quite used nowadays, so we use that in band M, and with band L, you twofold the number of channels. You should have a multiplexers. Everything has to be set up, but the industry is moving fast towards those changes. In the long run, multi-core fibers. You have a core and that cover. There you would have several cores in the same fibers. Here we have several cores in the same fiber with the same coverage. And different from what I asked in the beginning, we have the open fiber. That is the SDM, Spatial Division Multiplexing. Here we have a picture from DARP where they placed a light signal separated by some space where you have a huge capacity. Here the core, the center is air, so latency problem is solved here. 30% less latency, equivalent to a radio. This is just lab, okay? There is nothing under production, just some lab researches. When the light goes through air, we have a fiber attenuation around 3 to 4 dBs per kilometer. I had too many slides, sorry for being a bit longer. Well, very interesting talk. If there is any question to Tiago. Thank you.